Hi everyone and welcome to this video about processing the corona using JSol'Ex 3.3. So you will need of course JSol'Ex 3.3 but at least the version 3.3.1 or above, and you will need a lot of scans. And in this video I'm not going to talk too much about the scans themselves but more about the processing itself. And I'm going to start the processing right now, and then we're going to discuss what it does during the processing. So here you see that I have a lot of scans, 200 actually, and I took that today. And I'm going to ask JSol'Ex to process that while we are talking. So for this, I selected process, I use a custom process, and I'm using a script, which is the Corona script that you can find in the samples there. There's a slight modification on the script, but it shouldn't matter too much for these purposes. So let's start the process. And while it is doing that, I'm going to explain a bit how I did that. So first of all, let's take a look at one of these videos. So let's take a random one and let's look at the individual frames. So you can see that the video that we have here, so let's move a bit like on the 2/3 of the disk, I would say, something like that. It's clearer what we have on this spectrum. So we have a dark line here, which is detected by JSol'Ex, and this line is an iron line, iron 1. And it has a very specific wavelength, but this is not the line of the corona itself, because this line is just regular iron. There is a line which is actually much dimmer, like 1 million times dimmer than the actual photosphere, and it's called the ionized iron 14, and that line is below this one of a few pixels. And if you don't know, it's actually invisible, like you have no chance to see that. So the idea is basically to capture a lot of these frame like surf files, process them to extract this information, a bit like what we do for the helium line extraction. So we're going to take the line of the ionized corona line and subtract the continuum so that the signal is extracted. And then once we have that, we're going to stack everything. And this is done in a script. So let's go with the script and explain what it does. So if you do that, you won't have to change many things, basically. So what you need to do is to look at the parameters, and one thing which is important is that here I'm working with the actual wavelength description, so it's in angstroms, and it makes it super important for you to have specified here the in the observation details the size of the pixels of your camera and the instrument that you're using, because it's going to influence the dispersion. And basically JSol'Ex is going to compute the number of pixels between the reference line, so the dark line that I've shown before, which is the iron 1 line, which is at this wavelength, and it's going to compute how many pixels away this ionized line that we're interested in is. And then for extraction of the continuum, the subtraction actually of the continuum, we just take two absolute pixel shifts, like in pixels in the sky, and we're just going to compute the average of the continuum of these two different lines for the subtraction. So how does that work? It's actually fairly simple. So we have here a variable called shift, and this is where JSol'Ex is computing the pixel shift between this ionized line and the reference line that we see in the spectrum. So it's going to return a pixel shift, so a number of pixels. Then we have this offset, and I'm going to talk about that a bit later. And this is actually the line that I changed compared to the script that you have in JSol'Ex directly, but it shouldn't matter too much. In this case, it's a bit of denoising, if you will. So basically, instead of just taking the line right at the pixel shift where it should be, I'm taking a range from 0.5 pixels below to 0.5 pixels above, and with an interval of 0.5 pixels. So we're going to have 3 different images, and then I'm taking the maximum of these. And the maximum works quite nice, I think, and that's because of the Doppler effect, I think. So the ion line can, yeah, so because it's ionized 15 times, basically there can be a quite large difference in both directions, like the movement of the line in both directions. So having these increases the signal that you can extract. So this image that we call ion 14 is going to be the ionized line that we're interested in, and it's very, very dim. So what we need to do is actually to compute the continuum image, and in this case we're taking the image at the pixel shift that we computed plus these two values. So one image at -7 pixels, the other one at +4 pixels, and then we take the average of the two. So this is going to give us an average image of the continuum. And then what we generate for each of these files is basically a difference image, which is the ion image minus the continuum, and then we add an offset. And the offset is just to prevent the software from generating negative values, which would make things a bit more complicated to process. So to avoid that, we just add an offset. So we just make sure that there will be no negative values. So at this stage, we have the difference image, and what we are going to do is just to put a mask on the disk and then do a midterm transfer auto stretch on this. And this is really the key to having a successful corona image in the end. It is the auto stretch that we're going to apply, which is going to extract this signal. And so we're going to have one image called masked for each of the SIR files that we have in a sequence. So that's why here in my process you have all these masked image, and we have one per file. And if we look at one of these, you can see that there are regions which are actually brighter, and this is already signal from the corona. So the idea then is to do an average value of all these to extract the corona signal, and that's exactly what is done in the batch section. So if you're not familiar with scripts in JSol'Ex, basically there's a batch section which is executed at the end of this sequence. So once we have all the 200 files processed, then this is going to be executed, and it's going to take the equalized version of all the masked images, and that's because they don't all look exactly the same brightness. If you look at this list, it's not exactly the same brightness for all the images, so this is basically going to equalize the images. Then we're going to do reduce rescale to make sure that all the disks have the same size, a bit like what you need to do when you want to do stacking on AutoStacked, for example. And once we have that, basically we compute the average image, and boom, this is what we get. Actually, we get, after applying a disk and doing some square on the average image to increase the signal, we get this image, which is already nice, and we can see the corona here. And I think that not so many amateur images have seen so much details in the corona so far. So we have that, and then we have a second image, which is the rotated version. So we have the corona image, which is this image, and we apply a rotation in radians, which is the angle P, and we get this image. So these days the angle is very small, like 3 degrees or something like that, so that's why you only have a slight rotation of the image. And once this is done, I'm just drawing a legend on this just to put my name, and there you go. And of course we can try to improve the signal a bit, like we can do some curve stretching to try to extract more signal, like see where the corona is. Like this is not that bad. And well, if you want to, at this stage, you can actually tweak what happens in the batch section and try to see if you can improve the signal. So for example, I would do something like that, like create a second image that I'm going to call Corona 2, and maybe say, let's see if I can do some background removal. So remove background of the Corona, and because the signal is quite weak, let's not do that too strongly. So let's do a factor of 0.5 and run again. So it's going to compute these images again, and we have a second series. And now if I look at Corona 2, then it looks very close to what you have actually in the actual SDO image today. Like, it is impressive how close it is. And yeah, so this is basically just background removal, which can be a bit aggressive, but you can tweak that, or you can just not do that at all and do the stretching like I've done manually to extract the signal. But so yeah, so if you want to do some imaging, even if you if you have a Sol'Ex, or if you have SAG 700, the details that you're going to have to change are not very important. Basically, in this case, you're probably going to have to slightly change the continuum shift to tell where to find the continuum around the line. I could actually also use hard-coded values, like I could change the script to actually tell, well, we're going to search the continuum at these wavelengths, and that's it, and it's going to work also, and that would probably be easier for you. But yeah, so the only thing that which is really important is that you have set up again the parameters correctly in the observation details, like your instrument and the binning and the pixel size, because this is going to be important that JSol'Ex can compute this pixel shift. And well, yeah, that's all we have for today. I hope that you enjoyed that, and enjoy, and bye bye.